Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today I am going to discuss a nano finishing technique that is named as magneto-rheological abrasive flow finishing process, that is the MRAP process. Here Mr. Manas Das has contributed for this particular presentation. I acknowledge the PhD research work of Dr. Sunil Jha of IIT Delhi and Mr. Manas Das of IIT Kanpur, whose work has been quoted in this presentation. Organization of the talk is Introduction to MRAP process, MRAP experimental setup, rheology of MR polishing fluid, finishing results of MRAP process, development of R-MRAP process, and finishing results of flat and cylindrical workpieces, and then modeling and simulation of surface generation by MRAP process. Now we have seen in other lectures the abrasive flow finishing process or abrasive flow machining process and magneto-rheological finishing process. We have also discussed the limitations of magneto-rheological finishing process. It includes limited to finishing flat, spherical and aspherical external surfaces. So there is a shape limitation with MRF process, and standard MR polishing fluid are ineffective for polishing hard materials. So this is the material constraint in case of MRF process. Now let us recall limitations of abrasive flow machining process. It includes viscoelastic polymeric medium, which is costly, and lack of availability of the medium in India. Then viscosity of the polishing medium in case of AFM process is the most significant process parameter affecting AFM process performance. It varies in uncontrolled manner during the process. There is no online control of the rheological properties of the medium in AFM process. Hence there is a lack of determinism in case of AFM process. Keeping these limitations in view, a new process had been developed, and that process will be discussed in the following slides. So MRAP process, magneto-rheological abrasive flow finishing process, is the combination of magneto-rheological finishing and abrasive flow machining process. The viscosity of abrasive medium in MRAP process can be manipulated and controlled in real time. Hence it helps in deterministically and selectively abrading the workpiece surface. This is very important property of the medium in case of MRAP process, which has been taken from MRAP process. Then the use of machining setup similar to abrasive flow machining setup will remove shape limitation on workpiece surface to be finished, and this feature is taken from the abrasive flow machining process. So combining these two processes or hybridizing these two processes, we have a new process named as MRAFF process. This is the schematic diagram of MRAFF process. I will quickly explain this. Details will be discussed by Mr. Manas Das in the video film. Now here you can see that there is a top hydraulic cylinder, top MRF medium cylinder, and here is the workpiece which is to be finished, and then you have the connection to the power supply, because this is the electromagnet over here which is going to give different magnetic field depending upon the current flowing in the coils of this electromagnet. And here is the workpiece fixture that is shown there, and then you have the bottom magnetorheological polishing fluid cylinder over here, and this is the bottom hydraulic cylinder. Now what happens really here, that you fill the medium either in the top cylinder or in the bottom cylinder, mostly in the bottom cylinder, and then you place the workpiece between the top medium cylinder and bottom medium cylinder with the help of the tooling as shown over there. And once these two sections are connected and electromagnet is placed in place, then a hydraulic unit that pushes the piston inside the medium cylinder upward, so that whatever medium is filled in the bottom medium cylinder, that will be pushed upward and it will pass through the workpiece and workpiece tooling and come in the upper cylinder. And by the time this medium piston reaches to the top position, and then the direction of the flow of the hydraulic oil will change, and the medium from the top cylinder will start moving in the bottom cylinder. So up and down motion of the medium takes place through the workpiece, and when this workpiece comes in contact with the medium, then abrasive particles start upbraiding. As you can see here on the right hand side, these are the abrasive particles, and these are the chains which have been formed by the carbonyl iron particles or iron particles, and here is the north pole and south pole. So what happens when you bring this medium, as I will discuss later on, its constituent, then these iron particles or carbonyl iron particles arrange themselves along the magnetic lines of force, and they form the chains, and in between the chains or within the chains, abrasive particles which are shown here of the much bigger size, in real life they are not so, they are of the same size as the iron particles or carbonyl iron particles. And when these up and down movement takes place of this medium due to the hydraulic cylinder, then as you can see here, the abrasive particles, they rub the workpiece surface as shown over here, and the peaks of the workpiece surface, they are like this, they are sheared off. As a result, the surface roughness value of the workpiece surface goes down, and this up and down motion does shearing continuously of the peaks on the workpiece surface. And with this particular process, you can get around 50 nanometer surface roughness value. Now hydraulic unit is shown over here. This is the experimental setup that has been designed and fabricated at IIT Kanpur Manufacturing Science Lab. You can see some of the things visible over here. This is the hydraulic actuator which moves the piston in the MRP fluid up and down, and then here is the electromagnet, and between these two poles of electromagnet coils there is the workpiece which you cannot see very clearly, but I am showing it by arrow. And then this is the bottom medium cylinder, and here is the bottom hydraulic cylinder, and this is the hydraulic unit, and this is the regulated DC power supply which is used for this. And here you can say the panel or the board where through which you can control various parameters of the system. Electromagnet which creates the magnetic field surrounding the workpiece surface. In this particular process, you can see there are the two coils, coil 1 and coil 2, and here are the magnetic material which generates north pole and south pole, and in between this north pole and south pole there is a gap of 30 millimeter, and other dimensions are shown over there. The specifications of these coils are 2000 turns and wire is of 17 gauge. You can see the pictorial view of the same thing. Here are the electromagnet coils are there. You can see another view of the electromagnet. Here is the workpiece fixture. You keep the workpiece, this fixture is used for keeping the flat workpieces, and they can be kept in these two workpieces can be placed at one time. You can have more than 2 slots, then you can have more than 2 workpieces being finished at the same time. These are the shapes of the workpiece, and this is the pictorial view of this particular fixture, and you can see this workpiece gets fit over here. This is the one and this is for the second one. Then in some cases we use another workpieces, another shape and size of the workpieces like this, and there were different types of the fixture because size of these two workpieces are different. So fixture was separate one, as you can see over there. Now this is tooling which is connecting the workpiece with the medium cylinders. Now you can see the pictorial view of the tooling. MR polishing medium. This is the one of the main components or elements of the whole system, and magnetorheological fluids are suspension of micron sized magnetizable particles in non-magnetic carrier based fluid. Now this MR polishing medium consists following elements. One is the magnetic dispersed phase, which is nothing but either iron particles or carbonyl iron particles. Then continuous phase, that normally consists of oil, and then additives like grease is added as the additive to increase the density of the whole base medium, and then abrasive particles are added to this particular medium so that the finishing can be done, because carbonyl iron particles are used for forming the chain like structure which holds the abrasive particles, and abrasive particles are harder than the workpiece material, hence they are abrading or finishing the workpiece surface. The synthesis of the MR polishing fluid is like this: magnetic dispersed phase, that is the carbonyl iron particles, they are high purity 99.9 greater than 99.9% pure iron powder, and concentration normally taken is around 30%, but upper limit of this can be as high as 50%, which is rare. Particle size varies 10 to 30 micron size, and other choices are in place of carbonyl iron particles. They are very expensive. Then you can use iron cobalt alloy, and other one is ferrimagnetic materials like manganese zinc ferrite and nickel zinc ferrite. These are the different alternatives. So you have to choose the one depending upon the cost as well as the magnetic properties. Then there is the continuous phase. This continuous phase consists of organic liquids. Preferred continuous phase for MR fluids are silicone oil, kerosene, mineral oil, glycols or water, due to absorption of organic liquids on optical surface. Additives that are used includes additives are used to achieve stability against settling and enhance redispersibility. These two are very important properties actually, that when you are adding iron particles or carbonyl iron particles which are much heavier than the density of the base medium, that is the mineral oil and the grease. So what happens when you add them, then they try to settle down at the bottom, and we do not want settling down or sedimentation of the high density iron particles, otherwise finishing will not take place. So for minimizing this settling down and postponing this settling down, we use the additives for that particular purpose. And common additives are silica, fibrous carbon, and surfactants such as oleic acid. Now, abrasive particles also have density higher than the density of the base medium or liquid, and that settling down of abrasive particle is also not desirable. So, these additives helps in minimizing the settling down of abrasive particles as well as carbon iron particles or iron particle. Rheological characterization of MR polishing medium. The finishing efficiency and finishing quality of MRAP process relies mainly on the rheological properties, which are yield stress and viscosity of MR polishing fluid, which must be characterized before it is used in any specific application, because the performance of any medium will depend upon what is its yield strength and what is its viscosity on line, and it is desirable that both of these do not change during the process in an uncontrolled fashion, but we do not have any control on these properties in case of AFM process, abrasive flow machining process, but we have the control in case of magnetorheological finishing process, and that property has been taken in MRAP process. So, you can control the yield stress and viscosity externally by changing the magnetic field with the help of the current supplied to the electromagnet. These properties are responsible for bonding strength of abrasive particles surrounding the carbonyl iron particle chains. As I showed you in the earlier slide, that carbonyl iron particles form the chain, and these abrasive particles are either within the chain or between the chain, and the strength of these chains depends upon the magnetic field being applied over there. MRP fluid composition and volume ratio have an impact on rheological property and stability directly. What is the percentage of the carbonyl iron particles in the medium and what is the percentage of the abrasive particles in the medium? Both of them have a significant effect on the rheological properties of the MR polishing fluid, and the rheological properties of the fluid affect the performance of the MRAP process. Required to predict the effect of volume concentration of each component on yield stress and viscosity of MRP fluid, lot of study has gone into it about the effect of the percentage of carbonyl iron particles and percentage of abrasive particles on the yield stress of the medium and viscosity of the medium. Rheometer with magnetorheological device. Now, this is the rheometer which has been used for characterizing the MR polishing fluid, and this is Anton Farr MCR 301 parallel plate rheometer with MRD attachment. You can see sand blasted tool master is there, and then sand blasted measuring plate is over here. Now, the speciality of this plate is that this is sand blasted, so that the effect of abrasive particles on the plate is minimum, because the real life medium is consisting abrasive particles as well as iron particles. When you are evaluating their properties, then these particles are mixed in the medium and you are using them on this particular rheometer. So, it may damage the normal plate of the rheometer. So, special purpose plates, that is sand blasted plates, are used for the evaluation of the properties of the MR polishing fluid. Now, how it works, you can see here, this is the coil over there, here is the plate, upper plate is there, and then coil is there, because we are evaluating the properties of the MR polishing fluid under the magnetic field, because MRAP process uses the magnetic field during finishing. So, at different magnetic field strength, the fluid characteristics have been evaluated. So, you can see coils are there which create the certain magnetic field, and here is the MR polishing fluid, and when this plate rotates, shearing action takes place, and with the help of the data being provided by this rheometer, yield stress and the viscosity of a particular composition of the MR polishing fluid are evaluated. With the help of this rheometer, you can find out the properties of the medium at different shear rates. You can also vary the temperature of the medium, because during MRF process or AFM process or MRF process, the temperature of the medium changes as finishing keeps taking on. So, we should know the properties or rheological properties of the medium at different temperature also. So, you can utilize this particular rheometer for that purpose. Now, this is a very interesting picture. You can see here on the left side abrasive particles, iron particles randomly distributed in the medium, that is the base liquid which consists of oil as well as glycerol. But when you are applying the magnetic field, you can see columnar type of structure has been formed. You can clearly see these are the columns or the chains being formed, and here is the north pole and here is the south pole, and this is a specific characteristic, a special characteristic which helps in applying the force on the workpiece surface. And when these abrasive particles in these chains or between these chains come in contact with the workpiece, then they do the finishing, something very similar, close to what you do in case of grinding wheel. Here it works as a flexible grinding wheel. In the normal grinding wheel, you have the bonding material which is the fixed one, no flexibility is there. So, the MRP fluid is prepared by homogeneously mixing 26.6 volume percent of electrolytic iron powder and 13.4% silicon carbide abrasive of 150 mesh size with 48% paraffin oil and 12% AP3 grease that was used for this particular medium, for which picture is shown over here. Now, when the experiments were conducted using the medium in the MRF process, you can clearly see very interesting picture over here. This is the initial surface roughness in terms of micron RA value, as you can see here for different workpieces, 1, 2, 3, 4, 5 workpieces are there. Then finishing was done, and when finishing was done for a certain number of cycles, then you can see the surface roughness. This is magnetic flux density, and as the flux density is changing, here at 0 flux density there is no change in the RA value of the workpiece. When there is a certain magnetic field applied, then you can see there is a change from 0.48 RA value to the 0.44 RA value, and if you apply the higher magnetic field for the same number of cycles, then it changes from 0.49 to 0.43 micrometer RA value, and in the last but one case 0.48 to 0.38, and in the last case 0.47 to 0.34. So, actually magnetic field is clearly indicating its influence on the finishing rate, means per second or per cycle how much change in the RA value of the workpiece surface is taking place, and this is indicated by the blue color line, that as magnetic field is increasing, the change in the RA value is increasing continuously. And these are the details under which these experiments were performed. This is the polishing fluid, magnetic flux density 0.574 Tesla upper limit, and then extrusion pressure 3.75 megapascal, finishing cycles fixed 200, and workpiece material stainless steel workpiece, and the size is 35 by 5 by 2.5 millimeter. Surface roughness reduces with increase in magnetic flux density, as you can clearly see for same number of finishing cycles, extrusion pressure and MRP fluid. Now, then some of the pictures, SEM pictures were taken for the workpieces in the beginning before finishing, and you can see here this is the workpiece which has a 0.49 micrometer as RA value, and this is after grinding that was obtained with 0 magnetic field, and here you can see B is equal to 0.15 and finishing has been done, and you can clearly see the difference between the surf analyzer plots taken over here as well as in these SEM pictures also. You can clearly see that the peaks are sheared off, and these width of the peaks is increasing because continuously some of the peaks are being sheared off. So as you go down, as you can see here, as you shear off, then their width will keep increasing, which was this now, and earlier it was only this much. So that is what clearly you can see over here. Now if you increase the flux density, and you can see B is equal to 0.39 Tesla, RA value is 0.42, it further goes down, and at 0.53 Tesla it comes down to 0.53. You can clearly see the difference in these two figures. They have sheared large number of peaks, and it is becoming more or less the flat surface, and then you get 0.34, and you can see the difference in the last two figures. That means this is a better surface than this left hand side surface, and its RA value is 0.34 micrometer. So it clearly indicates the effect of magnetic field on the rate of finishing in case of MRF process. Now how it is working? If you see here, what is happening, that when there is no magnetic field, abrasive particles and iron particles are randomly distributed, and when you are pushing this medium forward, this is the abrasive particle, it just goes above the peak of the workpiece surface. This is the workpiece surface, and without removing any material, because there is no strength in the iron particle, or there is nothing which holds the abrasive particles and applies the force. So it just jumps and flows over the peak and comes out without any removal of material. But in the second case, where magnetic field is say 0.57 Tesla, then what is happening, you can clearly see the chains are being formed of the iron particles or CIP, and they are holding the abrasive particles between the chains. Here are the abrasive carbonyl iron particles or iron particles, they are holding the abrasive particle, and when you are pushing it in the direction of arrow as flow shown over here, then this abrasive particle will shear off the peak of the workpiece surface. It will depend upon what is the strength of the chains formed by the iron particles. So you can see in the second figure, it has removed a little amount of material from the peak of the workpiece surface, and this material is nothing but the chip. As you can see in the third figure, it has been removed, and it is called as the microchip or nano chip, depending upon the size of the chip. And this is how really the removal of the material takes place in MRF process. So it is nothing but mechanism of material removal in case of MRF process. So role of change in MRP fluid stiffness in response to magnetic flux density on surface finish improvement is clear. No finishing action at zero magnetic field, that I have shown here, B is equal to 0 T Tesla, and continuous improvement with the increase in magnetic field, that I have shown in the earlier slides also. Now here you can see the effect of extrusion pressure on surface roughness value RA. Now you can see here, this is the initial surface roughness and this is the final surface roughness. The difference between these two is given here by the blue color line, and you can see here clearly that there is not too much or not much effect of hydraulic extrusion pressure on the change in or RA value or final RA value that you are achieving. And these experiments have been done for 100 cycles at 0.53 Tesla is the magnetic field. Not much noticeable effect of extrusion pressure is found in experimental conditions. Low range of second point, you have to note that the variation that has taken place in the hydraulic extrusion pressure is definitely in low range, that is 1.25 megapascal only. But whatever is the range taken during experimentation, not much effect on RA value is obtained, that of hydraulic extrusion pressure. Optimum pressure in this particular case obtained is around 3.75 megapascal, as you can see here. Here is the maximum change delta Ra, here is the maximum change in Ra value. That is why for this range of pressure, this is the optimum value or the value which gives maximum delta Ra. Experimental results, effect of finishing cycles, you can clearly see here. This is for 300 cycles, this is the initial surface, this is after 300 cycles, this is 200 cycles, and this is 1000 cycles, and we clearly see that as this is the surf analyzer plot, we see that as the number of cycles is increasing, the surface roughness undulations are decreasing continuously. So, this is what you can see, this is the initial surface, this is the initial surface, and after certain number of cycles you can see the difference between this and this, that peaks have been sheared off and the width of the peaks is continuously increasing. Here it is further increased and sheared off, and only at larger intervals you are finding the valleys or the deep valleys, and the stylus movement is in this particular direction. Now you can see the difference in the surf analyzer plots after finishing and before finishing. Here is the initial surface, and this is after finishing with MRAP process, and you can see the surface finish that is obtained is about 30 nanometer after finishing, and other RQ and RY values are also given over there. So you can see you can get as good as 30 nanometer surface finish in case of MRAP process. Finishing conditions are given over here, which you can see, and the number of cycles used are 400 only. Now these are very interesting pictures. See here, this is the initial surface roughness after grinding operation, and this is the SEM photograph, and you can see what kind of peaks and valleys are there, and the surface roughness is 0.28 micron Ra value. Now if you see here, after 2000 cycles, the finishing has been done with the help of silicon carbide abrasive particles. Ra value from 0.28 has come to 0.10, but again you can see the surface quality or surface texture is not that good as it should be. So what we did, in place of SiC, we conducted some experiment with the diamond powder having the same properties, means same size and same again 2000 cycles, and you can clearly see again the surface roughness obtained is about 0.1 micron, but there is a difference in the surface quality obtained by diamond and that obtained by silicon carbide. Although diamond particles are very expensive compared to silicon carbide, but the surface quality improves, although surface roughness value may not decrease to a large extent. There are certain limitations of this MRAP process that I have just discussed to you, and these limitations are important to note. That low finishing rate, that can be expressed in terms of nanometer per cycle in general on hard materials. Difficult to provide uniform magnetic field in the finishing zone due to fixed coils at two diametrically opposite sides of cylindrical workpieces. Hence, non-uniform finishing of cylindrical workpiece at different points across the diameter will take place, which is again not desirable. So question is, what is the solution for these problems to resolve? So we have a solution that rotate the workpiece with respect to the fixed magnetic field. So what will happen when you are rotating? Then all the surface, whole surface of the workpiece will get uniformly finished, because whole area will pass through the high magnetic field, low magnetic field. So high magnetic field will give you the final surface finish, which is more or less uniform. Rotate the magnetic field with the help of permanent magnets or electromagnets. Now another point to note here is that normally people use electromagnet, but it is difficult to move or rotate the electromagnet. So in place of electromagnet we had used permanent magnet, so that the magnets can be rotated, and if you are rotating the magnet, then medium will be rotating with respect to the workpiece, and if medium is rotating with respect to the workpiece, it really does not matter whether you rotate the workpiece and medium is fixed, or you rotate the medium and workpiece is fixed, because what you need is the relative motion between the abrasive particle and the workpiece. So rotational magnetorheological abrasive flow finishing process was developed based on this particular principle, which I am going to explain in brief. Now system is the same as I have already explained to you, except that here you can see this is the belt drive, and here are the permanent magnets that have been fixed in the magnet fixture, and this whole device is rotated with the help of the AC motor, and the RPM, revolutions per minute, of this particular AC motor can be controlled by VFD, variable frequency drive. So what is really doing here is that you are rotating these permanent magnets with the help of the AC motor and the chain drive, and once these magnets are rotating, then due to the rotation of the magnet, magnetic field is rotating around the workpiece surface, and when magnetic field is rotating, then the medium is also rotating with respect to the workpiece surface. And this is the expanded view of the setup that has been developed for this particular purpose. You can see here these are the permanent magnets, this is the workpiece, this is the workpiece fixture, and you have gears etc. and connecting plates, and this is the permanent magnet which are shown over here, and when you rotate this, whole of this setup moves, and you can see here bottom medium fixture, and here is the top magnet holder or fixtures etc. are there. So you can have in place of this type of the you can have this type of the workpiece, or you can have the other type of the workpiece as I have shown to you in the earlier slide. Configuration of permanent magnets in RMRF process. This is an interesting figure. Now here you can see these are the three pictures that were taken by putting the magnets, permanent magnets, in three different ways. Configuration 1 you can see here, north north, south south. In case of configuration 2 you have north south and south north, and in configuration 3 you have only two magnets, south and north. And you can clearly see in all these three pictures that in the first configuration only you have the uniformly distributed medium all along the magnet, and the brush being formed is uniformly distributed. While in second configuration, you can see the magnet brush is formed and maybe stronger than what you have in case of 1, but this is not uniformly distributed. There are certain pockets where there is no brush, and there are other pockets where a strong brush is being formed. So in the third case we tried with two magnets only, and again the similar problem was there, that there are certain pockets where there are no brush being formed, and there are the certain areas where a strong brush is being formed, or continuous. You can see the chain from here one end to the another end is being formed, which you don't see in other two configurations. So it is strong but not uniform. That's why it was decided that configuration 1 is going to give better uniform surface finish as compared to configuration 2 and configuration 3. Hence configuration 1 was adopted. You can see here a schematic diagram, finishing principle of RMRF process. Now what is happening in RMRF process compared to MRF process? In MRF process, electromagnets or permanent magnets were fixed. So there was only axial motion of the medium due to the hydraulic upper cylinder or piston and hydraulic bottom piston. Here what is happening, that these magnets, four magnets are rotated as shown by the arrows over there, green color arrows, and there are magnetic clusters being formed. You can clearly see the magnetic particles and the abrasive particles, and these clusters are being formed, and when these magnets are rotating, then whole of this medium is also rotating, and once the medium is rotating, then there is a relative motion in rotating direction between the abrasive particle and the workpiece surface. And do not forget that this medium is continuously moving up and down due to the upper hydraulic cylinder and lower hydraulic cylinder. So there are two motions continuously taking place. One is the circular motion due to the rotation of the electromagnet, and another is the axial motion due to the movement of the piston of upper medium cylinder and piston of lower medium cylinder. As a result of these two motions, you get the helical motion of the abrasive particles. Now the question arises, what is the advantage of rotating the rotating the magnet so that you get helical motion of the abrasive particles with respect to the workpiece surface. Now that is shown over here with the help of the force diagrams. You can see on the left side you have the north and south poles, and here is the figure which shows the mechanism of material removal. Normal force is acting, and here is the axial force. Normal force is responsible for the penetration of the abrasive particle in the workpiece, and axial force is responsible for removal of the material from the workpiece in the form of micro nano chips. So there are only two forces that are acting, Fm as well as Fa, and material is being removed in the form of microchips. And if you see here on the right hand side figure, Fr is the resultant force, Fm is the magnetic force that is acting, and Fa is the axial force that is acting. But due to the extrusion pressure, axial force is there, but radial force is also acting at the same time. So there are the two forces, Fm and Fr, which are shown here. They are responsible for the penetration of the abrasive particle inside the workpiece. That is, this force here Fm is there, and here you have Fr also there. So both these forces are responsible for penetration, and axial force is responsible for removal of material in the form of the micro nano chip. But in case of RMRF process, if you see here, there is a rotation, and because of rotation two additional forces are acting. One is the centrifugal force, another is the Coriolis force. And you can see here that on the left side here is a picture, again chains are being formed of the iron particles, abrasive particles are there, and rotation is being given to the medium. Now here within the circle, if you see, there are various forces which are shown over there. Now if you see on the right hand side, the force, normal force that is responsible for the penetration of the abrasive particle into the workpiece is Fr, Fm. Here it is assumed that magnetic force that is acting is normal to the workpiece surface. Otherwise there will be a normal component of the magnetic force and axial component of the magnetic force, and then there is a centrifugal force. All the three forces are responsible for the penetration of the abrasive particle into the workpiece. On the other side there is a tangential force, because rotary motion is there. Due to the rotary motion, tangential force is acting on the abrasive particle, and there is the axial force due to the axial motion of the medium, and both these forces result in the Fc, that is the cutting force, and this cutting force is responsible for the removal of the material in the form of the micro nano chips. So this is how really you are getting that additional forces are acting on the abrasive particles. They increase the finishing rate in case of RMRF as compared to the MRF process, as we will see later on in the results. Now these are the equations which can be used for evaluation of the radial force, magnetic force, centrifugal force and tangential force, and total force that is responsible for indentation is given here, that vectorial sum of Fm, Fr and F centrifugal force, and the cutting force that is responsible for removal of the material, as you can see here, that is the vector sum of tangential force and axial force as shown over here. Indentation is due to the combined effect of magnetic, centrifugal and radial force, and cutting force is the resultant of tangential and axial force, as I have already explained. Path followed by the active abrasive particles on the workpiece surface is helical. This is important, as I have mentioned that helical path is being followed by the abrasive particles and covers more number of roughness peaks in one cycle. Why finishing rate is higher? Because when it is moving in a helical path in one single stroke, it will cover more number of the peaks, remove the material from more number of peaks, and total area where from material is being removed will be more than in case of MRAP process, and that is why you have higher finishing rate in case of RMRAP process as compared to MRAP process. Secondly, you get uniformly finished surface of the workpiece as compared to the MRAP process, and it is the operation something very similar to the honing process, where you have the cross hatch pattern. In this particular process also you get the cross hatch pattern, as I will show you later on with the help of the SEM photograph. It generates cross hatch pattern which helps in oil retention, especially in case of bearing etc., where oil should be retained in the bearing for minimizing or reducing the friction. This kind of cross hatch pattern surfaces are more useful rather than other surfaces. You can calculate the helix angle with the help of these equations given over here. Now this helix angle phi can be calculated by 2 pi c over 2 pi rw, or tan inverse c over rw, where c is given by Va over V omega and V omega is given by 2 pi n over 60. The arc length or the length being covered by the abrasive particle in RMRAF is bigger or larger compared to the case the length being covered by the abrasive particle in MRAF process. If you see in MRAF process, the workpiece is moving in a straight line up, down or up, but in case of RMRAF process, the workpiece is moving in the helical path like this, and when it is moving in the helical path like this, the total length covered by the abrasive particle, it is the abrasive particle which is rotating in the helical path. So the total length covered by an abrasive particle in the helical path is more than it is being covered in the straight line path as shown over here. So you can calculate the arc length of helical path. S is equal to HW over C multiplied by under root of RW square plus C square, and VA and V omega are axial and angular velocity of the polishing medium. This medium is rotating due to the rotation of the magnets. N is the rotational speed in revolution per minute. HW and RW are the height and radius of the workpiece that you can see over here. Here is the height HW and this is the radius of the workpiece, and that is shown over here by RW. Now this gives you an important information that total length of the workpiece is here. When you are rotating this magnet by 50 rpm, the calculated helical arc length is 44.33 millimeter. While you are rotating it by 250 rpm, this length increases to 60.89, and which is just approximately double of what you have the axial movement of the medium or the abrasive particle when there is no rotation for the magnets. At the same pressure, that is 37.5 bar, helical length of travel in case of MRAF is 43.5 millimeter, and which is lesser than RMRAF process, hence lesser polishing than MRAF. I am sorry, it is not double, but it is 1.5 times what you get at 250 rpm as compared to the axial or only MRAF process, which is 43.5 millimeter. Advantages of RMRAF process over MRAF process: uniform polishing throughout the workpiece surface due to the rotational motion of the polishing medium surrounding the workpiece surface. Then better control of the finishing forces through the control of the rotational speed of the polishing medium along with the existing reciprocating motion due to the hydraulic unit. The additional force other than the axial force acting on the abrasive particles due to its rotational motion of the magnet enhances the capability of the abrasive particles to abrade surface undulations from the hard workpieces like stainless steel. Due to the longer traverse length by the abrasive particles touching the workpiece surface because of helical path motion of the polishing medium in RMRF, which I have already explained. There is more interaction of the abrasive particles with the workpiece surface. Hence, better polishing than MRF process is achieved. Also, the finishing rate is also enhanced. Higher polishing rate or finishing rate in terms of nanometer per cycle as compared to MRF process due to the extra forces like centrifugal force and tangential force due to the rotational motion of the polishing medium and helical path motion of the polishing medium are obtained. In RMRF process, the abrasive cutting marks generate cross hatch pattern, which I have already shown to you, something like this. I will show you some pictures also on the finished surface of the workpiece, like in honing operation, traditional honing operation, which would improve the lubricant holding capabilities of the finished surface, and this is an important property in certain applications. Now you can see the experimental results over here, that change in RA, that is delta RA, which is nothing but the initial RA value minus final RA value or finished surface RA value. You can see three cases have been analyzed here. RPM of the magnet is changing, and here is the case of brass, stainless steel and EN8. Three different workpieces were taken. Two of them are non-magnetic, one of them is magnetic, that is the EN8 steel, and you can see some details are given here, effect of rotational speed of the magnet, and it was varied along like this on delta RA of brass, stainless steel and EN8 workpiece surface. Other conditions are given there. Now one thing you can see here, that almost in all the three cases there is some RPM where you are getting the maximum change in RA value, beyond which it starts decreasing. Now here again it gives the comparison of MRF and RMRF process. If you see on the last figure, this is the change in material removal, delta MR in terms of milligram, and it is low in case of this MRF process and it is more in case of RMRF process, and it is continuously increasing with increase in the RPM. And you can see in all the three workpiece materials, that is EN8, stainless steel and brass, this value is increasing whatsoever is small, and in case of brass this increase is maximum compared to other two materials. Now this is another interesting simulation that has been obtained, and you can see here, here are the magnetic field plot, comparison of magnetic field intensity. Now you can see here, this is the case where there is non-magnetic workpiece material, and you can see here is the magnetic MR magnetorheological polishing medium. This is the stainless steel workpiece, four workpieces are there at 90 degree, and this is the brass fixture is there which is non-magnetic, and the field applied is 0.23 Tesla. Now you can see the magnetic field is more or less uniformly distributed, but if you come here on the right hand side, magnetic flux, this 0.42 Tesla flux density, and important thing to note here is there is a large field intensity near to the workpiece, because these workpieces are magnetic materials, and what happens because of this, the abrasive particles penetrate inside the workpiece and there is not enough strength of the polishing medium that they can remove whole of the material. So either this rotates or the abrasive particles remains there intact, and you don't get good surface finish in case of magnetic workpiece material as compared to non-magnetic material. However, you can get much more faster finishing rate in case of magnetic material if axial force is large enough to remove whole of the material from whatever large penetration you have got in case of magnetic material. Now this is interesting figure, you can see here, this is the initial workpiece surface before finishing. You can see this is IIT K written over there, and this is the initial surface, and this is the atomic force micrograph, and this is surf analyzer. You can see the initial surface roughness is 330 nanometer and large peaks and valleys are there, and there is no reflection of the letter IIT K from the unfinished workpiece surface. When you finish this workpiece surface with the help of the RMRF process and you keep the same IIT K in the inverse way, you can clearly see the letter IIT K reflected just like a mirror on the workpiece surface, and this is the cross hatch pattern that has been obtained by RMRF process, and this is the atomic force micrograph that you can see clearly, and you can also see the difference between these two graphs or the surfaces clearly. And then surface roughness profile is there, and if you see this surface roughness profile of 16 nanometer, and here on the left side 330 nanometer, and it clearly indicates the finishing that has been achieved by RMRF process. And these are the SEM photographs which indicates initial surface over here, turned surface, then because these are the cylindrical workpieces which have been prepared on the lathe machine, and here is the RMRF process at 150 rpm, and you can clearly see the cross edge pattern like this as well as like this. They are clearly shown over here with the help of the arrows, and then RMRF process at 250 rpm, and there is an improvement in the surface finish to some extent, but cross edge pattern is still visible, and these figures have been taken at high magnification. You can see the scales given over here that will give you the idea for that. Now out of roundness, it is not only the finishing that you obtained, out of roundness of the cylindrical workpieces is also very important. So what we did, we took the out of roundness measure of the initial workpiece before finishing and then after finishing, and you can see clearly initially out of roundness was 5.17 micrometer, and after finishing it becomes 3.39 micrometer, and it was obtained at optimum finishing condition. Now let us discuss the modeling of chain structure that is formed in case of MRF process and RMRF process. This picture I have shown to you that in the absence of magnetic field, the abrasive particles and iron particles, they are randomly distributed. Here we have taken deliberately slightly larger abrasive particle, and you can clearly see that this is the abrasive particle which is there, and this is randomly distributed in the medium. Now when we apply the magnetic field, you can clearly see the difference in left hand side figure and right hand side figure. Proper chains are being formed, and these are the abrasive particle between the chains that you can clearly see, because abrasive particles are much bigger than the iron particles. We have taken them much bigger than the iron particles so that you can clearly see it, and these abrasive particles are lying between the chains, and these are the chains which are shining particles are there. So study of chain structure helps in understanding role of particle size on surface finish improvement. CIPs acquire magnetic dipole moment in the presence of external magnetic field and aggregate into chains of dipoles aligned in the field direction, as you can see here on the right hand side figure. These chains form columnar structure along the magnetic lines of force at higher concentration of carbonyl iron particles, and this columnar structure is very important, as you can see, because this is the one which gives the strength or shear strength to the medium, which is because of which it is able to remove the material. Modeling of chain structure has been done. Now this kind of chain structure has been assumed. All this will depend upon the concentration of the abrasive particle and concentration of the CIP or iron particles, and here is the SiC silicon carbide particle, and these are the iron particles or carbonyl iron particles, and you can see this is the kind of the structure that has been assumed theoretically. So iron particles rearrange around silicon carbide particles in the direction of magnetic field and repeat itself in a complete volume spanning from one end to the other end of the fixture between electromagnetic poles. Now here is the workpiece, on the other side also there will be the other side of the workpiece, and one pole will be here and another pole will be on this side, and this kind of structure is repeated from one side to the, or from one pole side to the another pole side. Now again this is very interesting picture. You can clearly see chain structure over there shining, and this is the direction of the magnetic field, and carbonyl iron particles are shining clearly, and then you can also see the silicon carbide particles over there, and here as shown over there, here the chain is terminating because silicon carbide particle has come in between the chain of the CIP. So this way CIP can be either within the chain, or silicon carbide may be either within the chain or between the chains, and this is very clearly shown in this particular picture. Due to the presence of non-magnetic abrasive particles in the MRP fluid, the chains are rarely continuous, as can be seen in this particular photograph. Instead terminate at the abrasive particles. If it comes in between the chain path, the same is observed under optical microscope over here. Now you can clearly see, using the models which was developed at IIT Kanpur, surface roughness simulation has been done, forces were calculated, and in this particular case this is the initial surface roughness, that is 0.28 micrometer, and this whole whole picture was taken from the surface analyzer data, and this is showing peaks and valleys of a particular surface. Now taking this peaks and valleys of the particular surface as the input to the simulation software, we simulated it, and you can see after simulation for a certain time for which finishing was done, the simulated results gave this particular output with a 0.19 micrometer as simulated final surface roughness value, RA value, and this is the picture of the simulated surface, and then finishing was done of the surface, finished surface, which was finished by RMRF process, and you can see the surface roughness value that was obtained was just 0.17 micrometer. So these two are not very far away, they are quite close to each other, simulated final RA value as well as measured RA value. And if you see this, the quality of these simulation here, the peaks and valleys are quite common in the measured surface as well as simulated surface. That simply indicates that simulation of the surface roughness is working very well, because wherever peaks are there, you can see peaks are there, valleys are there, and they are very well correlating with the measured surface. Hence this software works very nicely. Thank you very much.
I am Manas Das. I am doing PhD under Professor VKJ and Professor P.S. Ghosdostigar in rotational magnetorheological abrasive flow finishing process. Now I am going to demonstrate the experimental setup of magnetorheological abrasive flow finishing process. This is the experimental setup of magnetorheological abrasive flow finishing process. This setup has 4 different components. First component is that electromagnet and this core material, and second component is the hydraulic cylinder and media cylinder, and third component is the workpiece and workpiece fixture, and fourth component is the structure, whole structure of this MRFF setup. Main component of magnetorheological abrasive flow finishing process is the electromagnet. These are the 2 coils of electromagnet, and these are the core materials. Now I am explaining the electromagnet. The electromagnet, the design is made in such a way that it can generate 1 Tesla magnetic field. The dimension of this electromagnet is 160 millimeter and length is 150 millimeter, and it is a hollow electromagnet, is made of copper coil. Our coil has 2000 turn and it has 17 SWG copper wire and with square cross section. This electromagnet is designed in such a way that it will generate 1 Tesla magnetic field and it can take up to 10 ampere. The core material of this electromagnet, it is made of cold rolled anneal steel. The market name of this core material is Brightbird. It has 2 cylindrical cross sectional core which is inserted inside. This is the DC power source of this electromagnet. It can generate up to 10 ampere current to the electromagnet. Part of this magnetorheological abrasive flow finishing process is that hydraulic cylinder, and this is the media cylinder, and these two cylinders are there in the top side, and these two cylinders are there in the bottom side also. This is the hydraulic cylinder and this is the media cylinder. This is the workpiece fixture of MRFA process. It has three parts. The top guiding attachment is there to flow the polishing media from the top media cylinder to the workpiece fixture. Finishing zone of the magnetorheological abrasive flow finishing process. This workpiece fixture is made of brass materials. It has 4 internal slots to fix the workpieces. This is the hydraulic unit of MRFA process, which provide the pressure to the piston of MRFA process. This is the entry and this is the exit of the hydraulic fluid of MRFA process. It has a direction control valve which is connected to the solenoid, and it changes the direction of the fluid in the MRFF setup so that it can generate reciprocating motion, means from the top dead center to the bottom dead center, then the fluid will come from the bottom dead center to the top dead center. This is the hydraulic cylinder and this is the media cylinder. Inside this hydraulic cylinder, one piston is there, and inside this media cylinder, one Teflon piston is there, and these two pistons are connected by a connecting rod. When this hydraulic pump is activated, at that time this hydraulic fluid will come to the top entry of the pipe and it will press the piston in the hydraulic cylinder, and the fluid will come back to the bottom pipe and it will come to the blower hydraulic unit. By this process, reciprocating motion can be provided in the MRFA process. One Teflon piston is inside this medium cylinder, and inside this medium cylinder one stainless steel liner is kept. One counter is attached to the MRFF setup. It is provided to count the finishing cycle of MRFA process. Now I am showing how this reciprocating motion is provided in the MRFF setup. And this is the limit switch which is attached to the piston of medium cylinder, and it changes the current to the hydraulic unit, and the flow of fluid is reversed. The purpose of this limit switch is that it controls the stroke length of the piston in the medium cylinder. This is the workpiece fixture of MRFA process. It has two parts. One part is the top guiding attachment which is connected to the top media cylinder, and another part is the bottom guiding attachment which is connected to the bottom media cylinder. Inside these two guiding attachment, one brass fixture is attached, and inside this brass fixture 4 internal slots are there where flat workpieces are kept, and electromagnets codes are attached at these 2 points. Now I am showing how this reciprocating motion is provided to the Teflon piston inside the medium cylinder. See, this piston is reciprocating inside this medium cylinder at the bottom. This is the bottom medium cylinder. Now piston is given reciprocating motion to the top medium cylinder also. And this reciprocating motion of these two pistons are synchronized by a limit switch. The changes of the direction of the piston is controlled by a limit switch. See how this limit switch is activated now, and after this activation the direction of the piston is reversed. Main problem of MRFA process is non-uniform finishing of the workpiece, and also due to the reciprocating motion the abrasive particles comes in contact in a straight line path. So to increase the finishing efficiency of MRFA process and to uniformly polish the workpieces, rotational magnetorheological abrasive flow finishing is evolved. In rotational magnetorheological abrasive flow finishing process, permanent magnets are used. These are the permanent magnets which is rare earth permanent magnets. The scientific name of this permanent magnet is neodymium iron boron. This type of 4 permanent magnets is attached to this magnet fixture. This magnet fixture is connected to this pulley, and this pulley is connected to this motor via a positive belt drive. In RMFF process, this magnetic field is rotated via a permanent magnet, and this rotation is provided by a AC synchronous motor, and the rotational speed of this motor is controlled via a variable frequency drive. The accuracy of this drive is 2 RPM. See how these permanent magnets are rotated through a fixture, and inside this workpiece fixture the polishing media is given reciprocating motion. So there are 2 motions are there. One is this reciprocating motion and another is that rotational motion. MRFA process consists of magnetorheological polishing media. The magnetorheological polishing media consists of 4 different parts. First part is the base media. Base media consists of paraffin oil and grease. Instead of paraffin oil, we can use also silicon oil. And grease is used to increase the viscosity of the polishing media, and it reduces the sedimentation problem of MRFA process. The second part is the iron particles. Iron particles are 2 types. It can be carbonyl iron particles or it can be electrolytic iron particles. People all over the world are using carbonyl iron particles, CIP particles. It is manufactured by BSF Germany, and this is the electrolytic iron particles. It has bigger size, 250 to 300 mesh size. Part of magnetorheological polishing media is abrasive particles. Abrasive particles are maybe black silicon carbide or boron carbide or aluminum also can be used. Magnetorheological polishing media is prepared in this stirrer, and this is the container where this polishing media is prepared. Initially, this base media like paraffin oil and grease is put inside this container and it is stirred for half an hour. Then iron particles is poured inside this container and it is stirred for another half an hour, and then abrasive particles is put inside this container and this is stirred for another half an hour. This is the specially designed blade which is used for stirring of polishing media. This specially designed blade is connected to this stirrer, and this stirrer can be rotated at any RPM by a controller. By this way, a homogeneous mixture of magnetorheological polishing media is prepared inside this container. 2 different types of workpieces are finished by MRFA process. One is this flat workpieces and that is cylindrical workpieces. This is the initial surface of cylindrical workpieces which is finished by RMFA process. After finishing, you can see the internal surface of cylindrical stainless steel workpiece. This is the cylindrical workpiece fixture to fix the flat workpieces. It has 2 slots or 4 slots to fix the flat workpieces, and this is the fixture for fixing the square size flat workpieces. Magnetorheological abrasive flow finishing process is evolved as a new polishing process for finishing metallic workpieces. Surface roughness as well as 16 nanometer is achieved from cylindrical stainless steel workpieces. Thank you. I am Manas Das. I am doing PhD under Professor VKJ.